Tonight, we begin a gentle journey into one of the universe's most fundamental mysteries, a quiet truth that governs everything from the light reaching your eyes to the vast cosmic dance of galaxies billions of years away. Why does light have a speed limit? This isn't a story about rules imposed by some cosmic authority, but rather about the very fabric of reality itself. So settle in, perhaps dim the lights, and let us explore together this elegant limit that shapes everything we see, everything we are, and everything we can ever know. In the darkness of your room right now, photons are traveling toward you. They've journeyed from your phone screen, your bedside lamp, or perhaps the soft glow of streetlights filtering through your window. Each one of these particles of light is moving at exactly the same speed. Not approximately the same speed, not roughly the same speed, but precisely, invariably the same speed. 299,792,458 meters per second. This speed isn't arbitrary. It isn't a coincidence. It's woven into the very structure of space and time. To understand why light moves at this particular speed and why it cannot move faster, we must first understand what light actually is. Light is not a thing in the way we normally think of things. It's not matter. It has no mass. Instead, light is a traveling disturbance in something far more fundamental than matter itself. Light is a wave in the electromagnetic field that permeates all of space. Imagine, if you will, the surface of a perfectly still pond. When you drop a pebble into that water, ripples spread outward in concentric circles. The water itself doesn't travel with the wave. Instead, the wave is a pattern of motion that moves through the water. In much the same way, light is a pattern of motion that moves through the electromagnetic field. But unlike water waves, which need water to exist, electromagnetic waves can travel through the complete emptiness of space itself. This electromagnetic field exists everywhere. It fills the space between atoms in your body. It extends through the vacuum between Earth and the Moon. It reaches into the deepest voids between galaxies. And when this field oscillates, when it vibrates in just the right way, we get light. The speed at which these oscillations travel through space is what we call the speed of light. But why this particular speed? Why not faster? Why not slower? The answer lies in the fundamental properties of space and time themselves. The speed of light isn't really about light at all. It's about the maximum speed at which any information or influence can travel through the universe. Light simply happens to be massless, which means it naturally travels at this cosmic speed limit. Long before anyone understood the true nature of light, curious minds were trying to measure how fast it moved. For centuries, many believed that light traveled instantaneously. When you light a candle, the room illuminates immediately. When lightning flashes across the sky, you see it the moment it occurs. To our everyday experience, light seems to have no travel time at all. The first person to seriously question this was Galileo Galilei in the early 1600s. He proposed an experiment. Two people would stand on distant hilltops at night, each with a covered lantern. The first person would uncover their lantern. When the second person saw the flash, they would immediately uncover their own lantern. The first person would then measure how long it took to see the return signal. Galileo tried this experiment, but the distances were far too short and human reaction times far too slow to detect light's travel time. It wasn't until 1676 that a Danish astronomer named Ole Rømer made the first successful measurement of light's speed, and he did it by watching Jupiter's moons. Rømer noticed something peculiar about Io, one of Jupiter's largest moons. As Io orbited Jupiter, it would regularly pass behind the planet, disappearing from view. Rømer carefully timed these eclipses and noticed they didn't happen exactly when his calculations predicted they should. When Earth was moving away from Jupiter in its orbit, the eclipses occurred slightly later than expected. When Earth was moving toward Jupiter, they occurred slightly earlier. Rømer realized that this delay was caused by the finite speed of light. When Earth was farther from Jupiter, light from Io had to travel a greater distance to reach Earth, causing the apparent delay in the eclipse timing. From these observations, Rømer calculated that light traveled at roughly 200,000 kilometers per second. This was remarkably close to the true value, considering the tools available to him. More importantly, it proved that light does indeed have a finite speed. Over the following centuries, more precise measurements were made. In the 1800s, French physicist Hippolyte Fizeau used a rapidly rotating gear wheel to measure light's speed over terrestrial distances. Light would pass through the gaps between gear teeth, reflect off a distant mirror, and return. By carefully adjusting the wheel's rotation speed, Fizeau could time light's journey with unprecedented accuracy. But perhaps the most elegant measurement came from Albert Michelson in the early 1900s. Using precisely calibrated mirrors and rotating polygons, Michelson determined the speed of light to within a few parts per million of the value we accept today. His work was so precise that it earned him the Nobel Prize in Physics. These measurements all converged on the same remarkable truth. Light travels at a constant, unchanging speed through empty space. No matter how it's measured, no matter the direction it travels, no matter the motion of the observer making the measurement, light always moves at exactly the same speed. This constancy seemed impossible at first. After all, if you're riding in a car and throw a ball forward, the ball's speed relative to the ground is your car's speed plus the ball's throwing speed. Similarly, if you shine a flashlight while riding in that same car, you might expect the light's speed to be the normal speed of light plus your car's speed. But this doesn't happen. Light from your flashlight travels at exactly the same speed, whether you're standing still or racing down the highway at 100 kilometers per hour. This strange behavior puzzled physicists for decades. How could light always travel at the same speed, regardless of the motion of its source, or the observer measuring it? The answer came from Albert Einstein in 1905. In his special theory of relativity, Einstein realized that our intuitive understanding of space and time was fundamentally flawed. We tend to think of space and time as separate, absolute things. A meter is always a meter, a second is always a second. But Einstein showed that space and time are intimately connected, woven together into a four-dimensional fabric called space-time. And this fabric can stretch and contract depending on how fast you're moving. When you move very fast, time actually slows down for you relative to someone standing still. Distances contract in the direction you're traveling. These effects are normally imperceptible at everyday speeds, but they become dramatic as you approach the speed of light. It's these changes in space and time themselves that ensure light always travels at the same speed for all observers. Imagine you're on a train traveling very fast and you shine a flashlight forward. To you, on the train, the light travels away at the normal speed of light. But to someone standing on the platform, something remarkable happens. Your clocks are running slower due to your high speed. Your measuring sticks have contracted. When the person on the platform accounts for these changes in your space and time, they too measure the light traveling at exactly the normal speed of light. This isn't just a mathematical curiosity. It's been verified countless times in experiments. Particles in accelerators routinely travel at 99% of light speed or faster, and their behavior exactly matches Einstein's predictions. GPS satellites orbiting Earth must account for relativistic time dilation to maintain their accuracy. The constancy of light speed isn't just theory. It's measured reality. But why can't anything travel faster than light? The answer lies in what happens to matter as it approaches this cosmic speed limit. As any object with mass accelerates, it gains energy. At everyday speeds, this energy goes into increasing the object's velocity. But something strange happens as you approach light speed. More and more of the energy goes not into making the object faster, but into making it more massive. This isn't the object gaining matter. It's gaining what physicists call relativistic mass. The object's resistance to further acceleration increases dramatically. As you get closer and closer to light speed, it takes more and more energy to achieve smaller and smaller increases in velocity. To actually reach light speed would require infinite energy, which is impossible. Think of it like trying to push a boulder up an increasingly steep hill. At first, with modest effort, you can make good progress. But as the hill gets steeper, the same amount of pushing produces less and less forward motion. Near light speed, space-time itself becomes like an infinitely steep hill for any object with mass. Only massless particles can travel at light speed. Photons, the particles of light, have no mass at all. They don't experience this increasing resistance. In fact, from their perspective, they can only travel at light speed. A photon can never slow down, can never speed up. It exists only at this cosmic speed limit. This speed limit isn't just a curious feature of our universe. It's absolutely fundamental to how reality works. If light could travel faster, if information could move instantaneously across space, the very concepts of cause and effect would break down. Events could influence their own past. Effects could precede their causes. The logical structure of reality would collapse. Consider what would happen if you could send a signal faster than light. You could, in principle, send a message to your past self. You could warn yourself about mistakes you're about to make, create logical paradoxes where effects precede causes. The speed of light doesn't just limit how fast things can travel. It preserves the arrow of time itself. This cosmic speed limit also shapes the very structure of the universe we can observe. When we look up at the night sky, we're not seeing the universe as it is now. We're seeing it as it was when the light we're receiving first began its journey toward us. The star Sirius, one of the brightest stars in our sky, is about 8.5 light years away. The light reaching your eyes tonight actually left that star 8.5 years ago. The most distant galaxies we can observe are so far away that their light has been traveling toward us for over 13 billion years. We're seeing them as they were when the universe was young, when the first stars were just beginning to form. In a very real sense, astronomy is time travel. Every observation is a glimpse into the past, limited by light's finite speed. This creates what astronomers call the observable universe. Beyond a certain distance, light hasn't had enough time since the beginning of the universe to reach us yet. There may be galaxies, stars, and worlds beyond this cosmic horizon, but we can never see them as they are now. The speed of light creates a fundamental boundary to human knowledge. Within this boundary, light's constant speed creates a cosmic measuring stick. When we say a star is 100 light years away, we're using light itself as our unit of distance. We're saying it would take light 100 years to travel from that star to Earth. In this way, the speed of light connects distance and time in the most fundamental way possible. The electromagnetic waves we call light are just one small part of a much larger electromagnetic spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays and gamma rays are all electromagnetic radiation. They all travel at exactly the same speed through empty space. The only difference between them is their wavelength and frequency. When you listen to the radio, those radio waves traveled from the transmission tower to your receiver at light speed. When doctors take an X-ray, those X-rays travel at light speed through your body to the detector. When your microwave oven heats your food, It's using electromagnetic radiation at light speed to agitate water molecules. All electromagnetic radiation, regardless of its energy or wavelength, respects the same cosmic speed limit. This electromagnetic spectrum carries virtually all the information we have about the universe beyond our solar system. The light from distant stars tells us what they're made of, how hot they are, how fast they're moving. Radio waves from pulsars reveal the presence of incredibly dense neutron stars. X-rays from black holes show us matter being heated to millions of degrees as it spirals toward the event horizon. All of this information travels to us at light speed, creating a vast slow-motion movie of the cosmos. The speed of light also plays a crucial role in the fundamental forces that hold atoms together and govern the behavior of matter. The electromagnetic force, which keeps electrons bound to atomic nuclei and atoms bound together in molecules, is mediated by photons traveling at light speed. When atoms interact, when chemical bonds form and break, when electrical currents flow, all of these processes are governed by electromagnetic fields changing and propagating at light speed. Even the light you're seeing right now, whether from your screen or a nearby lamp, carries with it the history of its creation. If it's coming from an incandescent bulb, those photons were created when electrons in the tungsten filament lost energy and dropped to lower energy levels. If it's from an LED, the photons were created when electrons recombined with holes in a semiconductor material. In either case, the photons that eventually reached your eyes began their journey at the moment of their creation, traveling at light speed through the air to your retina. This journey happens so quickly at everyday distances that it seems instantaneous. Light can travel around the Earth's equator 7.5 times in just 1 second. It can travel from the Moon to Earth in about 1 1/3 seconds. From the Sun to Earth takes about 8 minutes and 20 seconds. These vast distances, incomprehensible in human terms, are traversed by light with elegant mathematical precision. Yet beneath this mathematical precision lies something even more profound. The speed of light emerges from the deepest properties of empty space itself. Even in the perfect vacuum between galaxies, where no matter exists for trillions upon trillions of kilometers, space is not truly empty. It hums with invisible fields, quantum fluctuations, and the fundamental constants that give our universe its character. Two of these constants in particular determine light's speed. The first is called the permeability of free space, which describes how easily magnetic fields can exist in vacuum. The second is the permittivity of free space, which describes how easily electric fields can exist in vacuum. These aren't arbitrary numbers. They're built into the fabric of reality itself, as fundamental as the dimensions of space or the flow of time. In the 1860s, Scottish physicist James Clerk Maxwell was studying electricity and magnetism when he made a startling discovery. His mathematical equations, which described how electric and magnetic fields behave, contained a surprising prediction. When he combined the permeability and permittivity of free space in a specific way, out came a velocity. That velocity was the speed of light. Maxwell's equations revealed that light is an electromagnetic wave, a self-sustaining dance between electric and magnetic fields. As an electric field changes, it creates a magnetic field. As that magnetic field changes, it creates a new electric field. This process continues indefinitely, with the disturbance propagating through space at a speed determined entirely by the electromagnetic properties of vacuum itself. This was one of the most elegant unifications in all of science. Light, electricity, and magnetism were not separate phenomena, but different aspects of a single, underlying field that permeates all of space. The speed at which electromagnetic disturbances travel through this field became a fundamental constant of nature, as basic and unchanging as the charge of an electron or the mass of a proton. But Maxwell's discovery raised new questions. If light is a wave, what medium does it travel through? Ocean waves need water. Sound waves need air. What does light need? For decades, physicists believed in an invisible substance called the luminiferous ether that filled all of space and carried light waves. This ether would have to be everywhere, perfectly transparent, and somehow not interfere with the motion of planets and stars. In the 1880s, two American physicists, Albert Michelson and Edward Morley, designed an ingenious experiment to detect this ether. They reasoned that as Earth moved through the ether during its orbit around the Sun, light traveling in different directions should have slightly different speeds, just as sound travels differently with and against the wind. Their apparatus used mirrors and beam splitters to send light along perpendicular paths and then recombine the beams to look for interference patterns that would reveal Earth's motion through the ether. They made their measurements with extraordinary precision, expecting to find clear evidence of our planet's movement through this cosmic medium. They found nothing. No matter how they oriented their apparatus, no matter when they conducted their experiment, light traveled at exactly the same speed in all directions. The absence of any ether wind effect was perhaps the most important negative result in the history of science. It suggested that the ether didn't exist at all, that light needed no medium to travel through. This null result puzzled physicists for years until Einstein provided the revolutionary insight that resolved the mystery. There is no ether because none is needed. Space and time themselves provide the stage for light's electromagnetic dance. The speed of light is not the speed of something moving through space, but rather the fundamental rate at which changes in information can propagate through the fabric of space-time itself. Einstein's special theory of relativity showed that this speed, this cosmic constant, is far more than just the velocity of electromagnetic waves. It represents the maximum speed at which any cause can produce an effect, the ultimate speed limit built into the structure of reality. Light happens to travel at this speed because photons are massless, not because there's something special about electromagnetic radiation itself. Imagine you're standing in a field on a calm day, and you clap your hands. The sound of that clap spreads outward in all directions as a spherical wave through the air. Now imagine that instead of sound, your clap somehow created a disturbance in space-time itself. That disturbance would spread outward as a sphere, but instead of traveling at the speed of sound, it would expand at the speed of light. This is closer to what actually happens when light is created. When an electron in an atom drops from a higher energy level to a lower one, it doesn't slowly release energy over time. The change happens essentially instantaneously, creating a kink or disturbance in the electromagnetic field surrounding the atom. This disturbance then propagates outward at light speed as a photon, carrying with it the exact amount of energy that the electron lost. The photon doesn't speed up gradually from rest to light speed. It's created already traveling at light speed and can never slow down. From the photon's perspective, if such a perspective makes sense, no time passes during its journey. It experiences its entire existence, from creation to absorption, as a single instant. Space and time contract to nothing along its path of motion. This timeless existence of photons reveals something profound about the nature of light speed itself. It's not that light chooses to travel at a particular velocity. Rather, light speed represents the natural rate at which massless disturbances propagate through space-time. It's the speed at which now becomes then, the rate at which the present moment expands outward to become the past. Consider what this means for causality, for the relationship between cause and effect. Every event in the universe creates a sphere of influence, expanding outward at light speed. Within this sphere, the event can potentially affect other events. Outside this sphere, the event might as well not have happened yet. The boundary of this sphere, expanding at light speed, represents the edge between the past and the future. If you could somehow travel faster than light, you could, in principle, arrive at a distant location before light from your departure point had time to get there. In a sense, you would arrive before you had left. The implications for causality would be devastating. Effects could precede their causes. The logical structure of reality would unravel. But the universe protects itself from such paradoxes through the energy requirements of acceleration. As any massive object approaches light speed, its kinetic energy increases without bound. The energy needed to accelerate a single electron to light speed would be infinite. No conceivable power source could provide such energy. This energy barrier isn't arbitrary or imposed by some external force. It emerges naturally from the geometry of space-time itself. Near light speed, space contracts and time dilates in such extreme ways that the normal relationship between energy and velocity breaks down. Energy that would normally increase velocity instead increases what we might call the object's inertial resistance to further acceleration. Think of it this way: as you approach light speed, you're not just fighting against your own mass. You're fighting against the structure of space-time itself, which increasingly resists any attempt to reach the forbidden velocity. The faster you go, the more energy is required for each additional increment of speed, until the energy requirement becomes infinite at light speed itself. Meanwhile, massless particles like photons experience none of this resistance. Having no mass, they have no choice but to travel at light speed. They cannot slow down, cannot speed up, cannot even come to rest. They exist only in motion, only at the cosmic speed limit, carrying energy and momentum, but never mass. This distinction between massive and massless particles reveals light speed to be more than just a velocity. It's a boundary in the space of all possible motions, a division between particles that can have rest frames and particles that cannot. Photons don't accelerate to light speed. They are created already at light speed and can exist nowhere else in the spectrum of possible velocities. The electromagnetic field itself, the medium through which light travels, fills every cubic centimeter of space with invisible potential. Even in regions we call vacuum, this field exists, ready to carry electromagnetic waves at its characteristic speed. The field's properties, encoded in those fundamental constants Maxwell discovered, determine not just light's velocity, but the strength of electromagnetic interactions throughout the universe. These same electromagnetic forces hold atoms together, allowing electrons to orbit atomic nuclei in stable patterns. They govern how atoms bond to form molecules, how chemical reactions proceed, how your neurons fire to create thoughts. The speed at which these electromagnetic influences propagate, the speed of light, sets the fundamental timescale for all atomic and molecular processes. When you see lightning flash across the sky, you're witnessing electromagnetic energy propagating at light speed through the atmosphere. The electrons in the lightning channel accelerate and decelerate so rapidly that they radiate electromagnetic waves across a broad spectrum, from radio waves to visible light to X-rays. All of these different wavelengths travel at exactly the same speed through space, forming the complex electromagnetic signature of the lightning bolt. This universality of light speed across all electromagnetic wavelengths reveals something beautiful about the underlying unity of nature. Radio telescopes detecting signals from distant galaxies, optical telescopes gathering starlight, and X-ray observatories studying black holes are all collecting the same fundamental phenomenon: electromagnetic radiation that has traveled across vast distances at the unchanging speed of light. The information carried by this radiation tells us about events that happened years, centuries, or even billions of years ago. When we observe the Andromeda Galaxy, the nearest large galaxy to our own Milky Way, we're seeing light that left those distant stars 2.5 million years ago. We're looking back through time to an era when our early human ancestors were just beginning to walk upright on the African savanna. This temporal aspect of astronomical observation means that the universe reveals itself to us as a vast, slow-motion movie of cosmic evolution. We can see galaxies as they were shortly after the Big Bang, when the universe was young and stars were just beginning to form. We can watch the life cycles of stars play out over millions of years. We can observe the collision of black holes that occurred billions of years in the past, their gravitational waves only now reaching our detectors. All of this cosmic cinema is made possible by light's finite speed. If light traveled infinitely fast, we would see the universe only as it is now, losing all access to its history. If light traveled much slower, the universe would appear frozen, with changes taking place too slowly for us to observe within human lifetimes. The actual speed of light provides the perfect temporal window for conscious beings like ourselves to study and understand the cosmos. Even the light reaching you from the sun carries with it a remarkable history of its journey. Each photon was created in the sun's core through nuclear fusion, where hydrogen nuclei combine to form helium, releasing energy in the process. But those photons don't immediately escape to travel toward Earth. Instead, they begin a random walk through the sun's interior, bouncing from atom to atom, absorbed and re-emitted countless times. This journey through the sun's interior can take hundreds of thousands of years. The photon that reaches your eye today may have been created during the time when humans were developing agriculture and building the first cities. Only when it finally reaches the sun's surface does the photon begin its 8-minute journey through space to Earth, traveling in a straight line at light speed through the near vacuum between worlds. This 8-minute delay means that the sun you see in the sky is the sun as it was 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know it for 8 minutes. Earth would continue orbiting around nothing, still feeling the sun's gravitational pull, until the last of the sun's light reached us and the sky went dark. But such dramatic events are purely hypothetical. In reality, the sun burns with steady, reliable fusion, converting 4 million tons of mass into energy every second, according to Einstein's famous equation, E equals mc squared. This energy radiates outward as electromagnetic waves at light speed, warming planets, driving weather systems, and powering the photosynthesis that sustains life on Earth. The constancy of light speed also enables one of the most precise measurement techniques in modern science, interferometry. When two light beams travel slightly different paths and then recombine, they create interference patterns that can detect incredibly tiny changes in distance. This principle allows us to measure the length of objects to within a fraction of a wavelength of light. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, uses this technique to detect gravitational waves from colliding black holes billions of light-years away. These waves stretch and compress space itself by amounts smaller than 1/10,000th the width of a proton. Yet because light speed is so precisely constant, LIGO can detect these minute changes in the length of its 4-kilometer arms. When two black holes spiral into each other and merge, they create ripples in space-time that propagate outward at light speed. These gravitational waves carry information about some of the most violent events in the universe, events that happened billions of years ago in distant galaxies. The waves travel across the cosmos for eons, finally reaching Earth where they cause infinitesimal changes in the distance between LIGO's mirrors. The fact that gravitational waves travel at light speed is itself a confirmation of Einstein's theories. According to general relativity, gravitational effects cannot propagate faster than light. If the sun were to suddenly disappear, Earth would continue in its orbit for 8 minutes until the gravitational disturbance reached us at light speed, the same moment that the sun's light stopped arriving. This speed limit for gravity has profound implications for our understanding of the universe. It means that massive objects cannot exert instantaneous forces on each other across space. Instead, gravitational influences propagate as waves in the fabric of space-time, traveling at the fundamental speed limit built into reality itself. The constancy of light's speed through vacuum also provides the foundation for our most precise definition of the meter. Since 1983, the meter has been officially defined as the distance light travels in vacuum during exactly 1 divided by 299,792,458 of a second. This definition makes the speed of light an exact number, precisely 299,792,458 meters per second by definition. This approach to measurement represents a shift from defining length using physical objects to defining it using fundamental constants of nature. The speed of light is so stable, so unchanging, that it makes a better standard than any human-made artifact. It connects our everyday measurements to the deepest properties of the universe itself. As we peer deeper into space with ever more powerful telescopes, light's finite speed creates a natural observatory of cosmic history. The most distant galaxies we can observe are so far away that their light has been traveling toward us for over 13 billion years, nearly the entire age of the universe. We're seeing them as they were when the universe was young, when the first stars were just beginning to illuminate the cosmic dark age. This creates what cosmologists call the observable universe, a sphere centered on Earth beyond which we cannot see because light hasn't had time to reach us yet. The radius of this sphere, measured in light travel time, is about 46 billion light-years. Beyond this cosmic horizon, there may be countless galaxies, stars, and worlds, but they remain forever invisible to us, hidden not by distance alone, but by time itself. Within this observable universe, every photon tells a story of its journey. Light from the nearest stars has traveled for just a few years. Light from distant galaxies in our local group has been traveling for millions of years. Light from the cosmic microwave background, the afterglow of the Big Bang itself, has been traveling for nearly 14 billion years, carrying with it information about the universe when it was only about 380,000 years old. This cosmic microwave background represents the oldest light we can observe, created when the universe had cooled enough for the first atoms to form. Before this epoch of recombination, the universe was opaque to light, a hot, dense plasma where photons couldn't travel far before being scattered by free electrons. The cosmic microwave background shows us the universe at the moment it became transparent, when light could finally travel freely through space. The temperature variations in this ancient light, tiny fluctuations of just a few parts per million, reveal the seeds of all the structure we see in the universe today. These quantum fluctuations, stretched by cosmic expansion and amplified by gravity over billions of years, eventually grew into galaxies, stars, and planets. The light that carries this information to us has been traveling at its constant speed since the universe was just a tiny fraction of its current age. Even the expansion of the universe itself is intimately connected to light's journey through space-time. As light travels from distant galaxies toward us, the expansion of space stretches the wavelengths of the photons, shifting them toward the red end of the spectrum. This cosmological redshift provides direct evidence for the expansion of the universe and allows us to measure how fast distant galaxies are moving away from us. The relationship between distance and recession velocity, known as Hubble's law, emerges directly from observations of this redshifted light. Galaxies that are twice as far away are moving away from us twice as fast. This linear relationship reveals that space itself is expanding uniformly, carrying galaxies along with it, like raisins in rising bread dough. Yet even in this expanding universe, light maintains its constant speed through local space. The photons themselves don't slow down or speed up. Rather, new space is created between their source and destination as they travel. This creates the paradox that we can observe galaxies that are now more than 14 billion light-years away, even though the universe is only about 14 billion years old. The light has been traveling for nearly 14 billion years, but during that time, the expansion of space has carried the source galaxy even farther away. These observations of distant light also allow us to study the history of cosmic expansion itself. By measuring the redshifts and distances of supernovae in distant galaxies, astronomers have discovered that the expansion of the universe is accelerating. This acceleration is attributed to dark energy, a mysterious component that makes up about 68% of the universe, but reveals itself only through its gravitational effects on cosmic expansion. The light from these distant supernovae, nuclear explosions that briefly outshine entire galaxies, carries information about cosmic expansion rates billions of years ago. By comparing these ancient expansion rates to more recent ones, we can trace the history of cosmic acceleration and try to understand the nature of dark energy itself. All of this cosmic detective work is made possible by light's unwavering constancy. Every measurement depends on the assumption that light traveled at the same speed in the distant past as it does today. If light speed had changed over cosmic time, our interpretations of astronomical observations would need to be completely revised. But tests of light speed constancy, both in laboratory experiments and astronomical observations, show that this fundamental constant has remained unchanged for billions of years. The light reaching us from quasars billions of light years away shows the same atomic spectral lines, shifted by cosmic expansion, but otherwise identical to what we observe in laboratory experiments today. This constancy extends to the fundamental forces and particles that govern the behavior of matter. The electromagnetic force that holds atoms together has the same strength in distant galaxies as it does on Earth. The masses and charges of electrons and protons appear to be identical throughout the observable universe. Light speed serves as a cosmic constant that helps maintain the stability of physical law across space and time. In the deepest sense, the speed of light represents the rate at which reality itself unfolds. It's the speed at which the future becomes the present, and the present becomes the past. It determines how quickly information can flow from one part of the universe to another, setting the fundamental pace of cosmic evolution. This cosmic speed limit creates what physicists call light cones, geometric structures in space-time that define the boundaries between past, present, and future for any given event. Every moment in your life sits at the apex of two cones, one extending into the past, containing all the events that could have influenced your present moment, and another extending into the future, containing all the events your present moment could potentially influence. The slopes of these light cones are determined by the speed of light. Nothing can travel faster than light, so no information or influence can cross from outside your light cone to affect your present moment. Similarly, your actions now can only influence events that lie within your future light cone. In this way, light speed creates the causal structure of space-time, defining the very meaning of before and after. As you rest here in the quiet darkness, photons are still arriving at your eyes. Each one carrying its own story of creation and journey. Some were emitted from artificial lights just meters away. Others may be starlight that has traveled for years or decades across interstellar space. Each photon, regardless of its origin, travels at exactly the same speed, following the fundamental law that governs the flow of information through our universe. This speed limit of light isn't a restriction imposed by some external authority. It's an expression of the deepest symmetries and structures of space-time itself. It emerges naturally from the requirement that physical laws be the same for all observers, regardless of their state of motion. It ensures that cause precedes effect, that information flows in a logical sequence from past to future. In contemplating light's speed limit, we encounter one of the most elegant truths about our universe, that its fundamental laws are not arbitrary rules, but necessary consequences of deeper principles of symmetry and causality. The speed of light connects space and time, matter and energy, cause and effect in ways that make our universe logically coherent and mathematically beautiful. This cosmic speed limit defines the ultimate horizon of human knowledge and influence. We can never know about events happening right now in distant galaxies. We can never send signals that travel faster than light. We are forever embedded in our local patch of space-time, connected to the rest of the universe only by the patient, constant flow of light and other massless particles across the cosmic void. Yet within these constraints, light enables the rich tapestry of observation and discovery that defines modern astronomy and physics. It carries to us the stories of stellar birth and death, of galactic collisions and cosmic evolution, of the fundamental particles and forces that shape reality at the smallest scales. Through light, we participate in the grand conversation of the cosmos, listening to messages that have traveled across space and time to reach us. As the gentle flow of photons continues to reach your eyes in the soft darkness, consider that you are directly experiencing one of the universe's most fundamental phenomena. The light that allows you to see is the same electromagnetic radiation that carries information from the most distant galaxies, that mediates the forces holding atoms together, that sets the ultimate speed limit for all physical processes. In its constant, unwavering velocity, light embodies the mathematical precision and elegant simplicity that underlies all of physics. It reminds us that our universe operates according to deep, beautiful principles that connect the smallest scales of quantum mechanics to the largest scales of cosmology. The speed of light is not just a number in physics textbooks. It's a window into the fundamental nature of existence itself, traveling through space and time to bring the universe home to our waiting eyes. The dance between light and space-time becomes even more profound when we consider how this cosmic speed limit shapes the very architecture of atoms themselves. In the quiet spaces between atomic nuclei and their orbiting electrons, electromagnetic forces operate at light speed, creating the stable patterns of matter that form your body, the air you breathe, and everything you touch. When an electron absorbs energy and jumps to a higher orbital, the electromagnetic field around the atom doesn't instantly adjust to this new configuration. Instead, the change propagates outward at light speed, like ripples spreading across the surface of a still pond. This fundamental delay, measured in attoseconds, helps determine the precise timing of chemical reactions and the stability of molecular bonds. The same electromagnetic waves that carry this information between particles also carry the thermal radiation that warms your skin. Every object with a temperature above absolute zero emits electromagnetic radiation according to its thermal energy. The gentle warmth you might feel from a nearby radiator travels to you as infrared photons, each one journeying at light speed across the small distance between source and skin. These thermal photons tell a story of energy in motion. Deep within the heating element, electrical resistance converts the flow of electrons into kinetic energy. causing atoms to vibrate more rapidly. As these excited atoms settle back to lower energy states, they release photons that carry away the excess energy. The photons stream outward through space, maintaining their constant velocity until they encounter your body and transfer their energy to the molecules in your skin. This transfer happens through the photoelectric effect, the same phenomenon that earned Einstein his Nobel Prize. When a photon strikes an electron in your skin, it can transfer all of its energy instantaneously, causing the electron to move to a higher energy state. This absorbed energy then converts to the gentle sensation of warmth, completing a chain of energy transformation that began with electrical current and ended with your direct experience of electromagnetic radiation. The precision of this energy transfer depends entirely on light's constant speed. If electromagnetic radiation could travel at variable velocities, the timing of atomic interactions would become chaotic. Chemical bonds would form and break unpredictably. The delicate energy balances that maintain biological processes would collapse into disorder. Instead, the unwavering constancy of light speed creates a reliable temporal framework for all electromagnetic interactions. Every photon, whether carrying the energy of visible light, infrared warmth, or radio waves, follows the same universal schedule. This temporal precision allows complex molecules to maintain their structure and enables the intricate choreography of biochemical processes that sustain life. In the darkness around you, countless electromagnetic interactions are occurring with clockwork regularity. The molecules in the air vibrate and rotate, absorbing and emitting infrared radiation in a continuous dance of energy exchange. Each photon in this invisible ballet travels at exactly the same speed, creating a thermal equilibrium that maintains the comfortable temperature of your environment. The walls of your room participate in this thermal dance as well. Throughout the day, they absorbed electromagnetic radiation from various sources, storing thermal energy in the motion of their constituent atoms. Now, in the quiet evening, they slowly release this energy as infrared photons that travel at light speed through the air, contributing to the gentle warmth that surrounds you. This thermal radiation follows the same electromagnetic principles that govern visible light, radio waves, and X-rays. The only difference lies in the wavelength and frequency of the oscillating electromagnetic field. Infrared radiation has longer wavelengths than visible light, making it invisible to human eyes, but readily detectable by the thermal sensors in your skin. The relationship between wavelength and frequency remains constant for all electromagnetic radiation, connected by the speed of light through a simple but profound equation. As wavelength increases, frequency decreases in perfect inverse proportion, ensuring that their product always equals the speed of light. This mathematical relationship unifies all forms of electromagnetic radiation under a single, elegant framework. Radio telescopes scattered across Earth's surface detect this same relationship in the cosmic microwave background, the afterglow of the Big Bang that fills all of space. These ancient photons, stretched by billions of years of cosmic expansion, now have wavelengths measured in millimeters rather than the visible light wavelengths measured in nanometers. Yet they travel at exactly the same speed as the light reaching your eyes from a nearby lamp. The stretching of these cosmic photons reveals another profound connection between light speed and the structure of space-time. As the universe expands, it doesn't push galaxies apart through empty space. Instead, space itself grows larger, carrying galaxies along like markers on an inflating balloon. The photons traveling through this expanding space experience a gradual stretching of their wavelengths, a process that preserves their speed while changing their color. This cosmological redshift provides direct observational evidence for the expansion of the universe. By measuring how much the wavelengths of distant starlight have been stretched, astronomers can determine both the distance to remote galaxies and the rate at which space itself is expanding. These measurements reveal that galaxies farther away are receding faster, exactly as predicted by the equations of general relativity. The mathematical relationship between distance and recession velocity, encoded in Hubble's constant, allows us to trace the expansion of the universe backward through time. Following this cosmic rewind, we arrive at a moment roughly 14 billion years ago, when all the matter and energy in the observable universe was concentrated in an incredibly hot, dense state. This moment marks the beginning of the Big Bang, the event that set the cosmic expansion in motion. Light speed provides the fundamental timescale for this cosmic evolution. The age of the universe, measured in years, multiplied by the speed of light, gives us the radius of the observable universe in light years. This cosmic horizon represents the farthest distance from which light has had time to reach us since the beginning of time itself. Beyond this horizon lies a realm forever hidden from direct observation. There may be countless galaxies, stars, and worlds in these unreachable regions, but their light hasn't had sufficient time to traverse the vast distances of space. The finite speed of light creates a fundamental boundary to human knowledge, defining the edge of everything we can ever hope to see or study directly. Within our observable universe, light's constant speed enables precise measurements of cosmic distances. Astronomers use standard candles, objects with known intrinsic brightness, to gauge the distances to remote galaxies. By comparing the apparent brightness of these objects to their known luminosity, they can calculate how far the light has traveled to reach our telescopes. Type Ia supernovae serve as particularly reliable standard candles because they represent the explosion of white dwarf stars that have accumulated matter from companion stars until they reach a critical mass. This critical mass is determined by fundamental physics, ensuring that all type Ia supernovae release approximately the same amount of energy and achieve similar peak brightness. When astronomers observe these stellar explosions in distant galaxies, they're seeing events that occurred millions or billions of years ago. The light from the supernova began its journey toward Earth at the moment of the explosion, traveling at light speed across the vast emptiness between galaxies. The precise timing of this journey allows astronomers to study not just the distance to the host galaxy, but also the rate of cosmic expansion when the supernova occurred. These observations have revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Distant supernovae appear dimmer than expected based on their redshift, indicating that they're farther away than they would be in a universe expanding at a constant rate. This acceleration is attributed to dark energy, a mysterious component that comprises about 68% of the universe, but manifests only through its gravitational effects. Dark energy appears to act as a kind of cosmic anti-gravity, pushing space apart with increasing strength as the universe grows larger. Despite its dominance in the cosmic energy budget, dark energy remains one of the greatest mysteries in physics. We know of its existence only through its effects on the expansion of space, revealed by the carefully measured journeys of ancient photons across cosmic time. These same photons carry information about the fundamental forces and particles that governed the universe billions of years ago. The spectral lines in starlight from distant galaxies reveal the same atomic transitions we observe in laboratory experiments today. Hydrogen atoms in galaxies 10 billion light-years away emit and absorb photons at precisely the same wavelengths as hydrogen atoms on Earth. This constancy of atomic spectra across cosmic space and time provides powerful evidence that the fundamental constants of nature have remained unchanged throughout the history of the universe. The electromagnetic force that binds electrons to atomic nuclei appears to have exactly the same strength in distant galaxies as it does in our local region of space. The precision of these measurements depends entirely on the constancy of light speed. If electromagnetic radiation traveled at different velocities in different regions of space, or at different epochs in cosmic history, the apparent wavelengths of spectral lines would vary in unpredictable ways. The fact that we observe consistent atomic spectra throughout the observable universe confirms that light has maintained its characteristic speed across billions of years of cosmic evolution. This temporal consistency extends to the fundamental structure of space-time itself. Einstein's equations of general relativity describe how matter and energy curve the fabric of space and time, creating the gravitational forces we experience. These equations predict that gravitational influences, like electromagnetic ones, propagate at light speed through the cosmos. When massive objects accelerate, they create ripples in space-time that travel outward as gravitational waves at exactly the speed of light. These waves carry energy away from their sources, causing orbiting objects to gradually spiral inward as they lose energy to gravitational radiation. The detection of these waves by observatories like LIGO provides direct confirmation of Einstein's predictions and reveals the speed limit that governs even the force of gravity itself. The merger of two black holes, events so violent they can briefly outshine all the stars in the observable universe in gravitational wave energy, creates ripples in space-time that propagate across billions of light years at precisely light speed. When these waves finally reach Earth, they cause infinitesimal changes in the length of LIGO's detection arms, stretching and compressing space itself by amounts smaller than 1,000th the width of a proton. The ability to detect such minute distortions depends on the extraordinary constancy of light speed. LIGO operates by comparing the travel time of laser light along perpendicular arms of equal length. When a gravitational wave passes through the detector, it temporarily changes the length of these arms by different amounts, causing the laser beams to fall slightly out of phase when they recombine. This interference effect creates a measurable signal that reveals not just the presence of gravitational waves, but detailed information about their sources. The frequency and amplitude of the waves encode the masses of the merging objects, their orbital dynamics, and their distance from Earth. All of this information travels to us at light speed, carried by the fundamental geometry of space-time itself. The detection of gravitational waves opened an entirely new window on the universe, one that complements the information carried by electromagnetic radiation. While light can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through material obstacles essentially unimpeded. They carry pristine information about events occurring in the most extreme environments in the universe. When two neutron stars spiral into each other and merge, they create both gravitational waves and a brilliant flash of electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. The gravitational waves travel at light speed through space, unaffected by any matter they encounter along the way. The electromagnetic radiation, also traveling at light speed, follows the same path, but may be absorbed or scattered by gas and dust clouds between the source and Earth. By detecting both signals simultaneously, astronomers can study the same cosmic event through multiple channels of information, each traveling at the fundamental speed limit of space-time. This multi-messenger astronomy provides unprecedented insights into the physics of extreme matter, the origin of heavy elements, and the expansion rate of the universe itself. The creation of heavy elements in neutron star mergers illustrates another profound connection between light speed and the structure of matter. When neutron stars collide, they create conditions of such extreme temperature and density that rapid neutron capture can build atomic nuclei far heavier than iron. This IR process nucleosynthesis occurs on timescales comparable to the neutron beta decay lifetime, creating unstable isotopes that quickly decay into stable heavy elements. The electromagnetic radiation produced by these newly formed heavy elements escapes the merger site at light speed, carrying spectroscopic signatures that reveal the chemical composition of the ejected material. These observations confirm that neutron star mergers are likely sources of many of the heaviest elements found in nature, including gold, platinum, and uranium. The gold in any jewelry you might be wearing was likely forged in such a cosmic collision billions of years ago. Its atoms assembled through rapid neutron capture in conditions of unimaginable violence. The photons that first announced this creation event began their journey across space at light speed, though they may have been absorbed and re-emitted countless times before reaching the gas and dust cloud that eventually collapsed to form our solar system. This cosmic recycling of matter depends fundamentally on light's ability to carry energy away from stellar cores and explosive events. When massive stars exhaust their nuclear fuel and collapse into supernovae, the enormous energy release drives material outward into interstellar space at velocities that can reach significant fractions of light speed. This expelled matter, enriched with heavy elements created during the star's lifetime and final explosion, eventually forms new generations of stars and planets. The radiation pressure from intense starlight plays a crucial role in this process. In the most massive stars, the outward pressure from electromagnetic radiation can overcome gravitational attraction, driving stellar winds that carry away significant amounts of stellar material. These radiatively driven winds travel at speeds determined by the balance between gravitational attraction and radiation pressure, both of which propagate at light speed through the stellar atmosphere. The intricate feedback between gravity, radiation, and matter in stellar interiors creates the stable fusion reactions that power stars for billions of years. In the sun's core, hydrogen nuclei overcome their electrical repulsion through quantum tunneling, fusing to form helium and releasing energy in the form of gamma rays. These high-energy photons begin a random walk through the sun's interior, being absorbed and re-emitted countless times as they gradually work their way toward the surface. Each absorption and re-emission event occurs at light speed, but the photon's path becomes a three-dimensional random walk that can take hundreds of thousands of years to complete. The photon that reaches your eye tonight may have been created in the sun's core during the time when human civilization was developing agriculture and building its first cities. Only when the photon finally reaches the sun's surface does it begin its direct 8-minute journey through space to Earth. This delayed energy transport creates a natural thermostat that regulates stellar fusion. If fusion rates increase, the additional gamma rays create higher radiation pressure, causing the stellar core to expand and cool, which reduces fusion rates back toward equilibrium. If fusion rates decrease, the reduced radiation pressure allows gravity to compress the core, raising temperatures and increasing fusion rates. This self-regulating process maintains stable energy output for billions of years. The balance between radiation pressure and gravitational compression also determines the ultimate fate of stars. When nuclear fuel is exhausted, radiation pressure can no longer support the star against its own gravity. For stars like the Sun, the core will eventually collapse to form a white dwarf, supported by electron degeneracy pressure. For more massive stars, the collapse can overcome even this quantum resistance, creating neutron stars or black holes. In the most extreme case, when a stellar core exceeds about 3 solar masses, no known force can halt the gravitational collapse. The matter falls inward at ever-increasing speed, eventually reaching velocities approaching light speed near the forming event horizon. At this boundary, the escape velocity equals the speed of light itself, creating a region of space-time from which no information can ever escape. The event horizon represents a fundamental boundary in space-time, defined entirely by the cosmic speed limit. Outside this radius, light can still escape the gravitational field, though it becomes increasingly redshifted as it climbs out of the deep gravitational well. Exactly at the event horizon, light requires infinite time to escape. effectively freezing at the boundary from the perspective of distant observers. This gravitational time dilation near black holes provides another dramatic illustration of how light speed connects space and time. As matter falls toward the event horizon, it experiences increasingly strong gravitational fields that slow the passage of time relative to distant observers. Light emitted by the falling matter becomes progressively more redshifted and dimmed until the source effectively fades from view at the event horizon. The mathematics describing this process emerged directly from Einstein's insight that space and time form a unified four-dimensional fabric that can be curved by matter and energy. The speed of light appears in these equations not as an arbitrary constant, but as the fundamental conversion factor between space and time coordinates. It determines how much time corresponds to a given distance in the geometry of space-time. This geometric interpretation reveals why the speed of light must be the same for all observers regardless of their motion. The geometry of space-time itself ensures that the interval between any two events, measured using the space-time metric, remains invariant for all observers. Different observers may disagree about the spatial distance or time interval between events, but they will always agree on the space-time interval calculated using the speed of light. This invariance of the space-time interval provides the mathematical foundation for all of special and general relativity. It explains why moving clocks run slow, why fast-moving objects contract in length, and why gravity can be understood as the curvature of space-time itself. All of these seemingly mysterious effects emerge naturally from the requirement that the laws of physics respect the fundamental symmetries of space-time. The speed of light thus serves as more than just the velocity of electromagnetic radiation. It represents the fundamental metric of space-time, the conversion factor that allows us to measure space and time using the same units. In natural units used by physicists, the speed of light is often set equal to 1, making explicit the deep unity between spatial and temporal measurements. This unity becomes apparent when we consider how light travels through the universe. A photon emitted by a distant star doesn't just traverse space, it travels through space-time itself, following a path called a null geodesic that represents the shortest distance between two events for a massless particle. From the photon's perspective, its entire journey occurs instantaneously, with both space and time contracted to zero along its path of motion. This timeless existence of light reveals something profound about the nature of electromagnetic radiation. Photons don't experience the passage of time as we understand it. They exist in an eternal present, connecting distant regions of space-time through paths that transcend the normal flow of temporal experience. In a sense, light serves as the universe's method for maintaining simultaneity across vast distances, carrying information instantaneously from its own reference frame, while respecting causality in all other frames. The cosmic microwave background radiation provides a beautiful example of this temporal transcendence. These ancient photons, released when the universe became transparent about 380,000 years after the Big Bang, have been traveling through space for nearly 14 billion years from our perspective. Yet from the photon's own reference frame, their entire journey from the surface of last scattering to your microwave detector occurs in a single, timeless instant. These relic photons carry with them a snapshot of the universe at the moment of their creation, when the cosmos was a hot, dense plasma cooling rapidly as space expanded. The tiny temperature fluctuations preserved in this ancient light reveal the quantum fluctuations that eventually grew into galaxies, stars, and planets through the action of gravity operating over cosmic time. The detection of these fluctuations requires extraordinary precision, as the temperature variations amount to only a few parts per million. Satellite observatories like the Cosmic Microwave Background Explorer and the Planck mission have mapped these tiny variations across the entire sky, creating detailed portraits of the universe when it was less than 1% of its current age. The angular scale of these temperature fluctuations depends on the fundamental geometry of space-time and the expansion history of the universe. The largest fluctuations correspond to regions that were in causal contact at the time of last scattering, bounded by the distance light could travel during the 380,000 years between the Big Bang and recombination. This acoustic horizon in the early universe created a characteristic scale for density fluctuations that we can still observe today in the cosmic microwave background. The measurement of this scale provides one of the most precise determinations of cosmological parameters, including the age, composition, and geometry of the universe itself. These measurements reveal that we live in a flat universe, one whose geometry follows the familiar rules of Euclidean space on the largest scales. This flatness is remarkable because it requires the total energy density of the universe to equal a critical value determined by the expansion rate and the fundamental constants of gravity. Any significant deviation from this critical density would cause space to curve either positively or negatively, creating observable effects in the cosmic microwave background. The precision required to achieve this flatness suggests that the early universe underwent a period of rapid, exponential expansion called cosmic inflation. During this brief epoch, quantum fluctuations were stretched to enormous scales, creating the nearly uniform conditions we observe today, while preserving tiny variations that seeded all subsequent structure formation. Inflation theory predicts that gravitational waves should also have been produced during this primordial expansion, creating a specific pattern of polarization in the cosmic microwave background. The detection of these primordial gravitational waves would provide direct evidence for inflation and offer insights into physics at energy scales far beyond anything achievable in terrestrial laboratories. These cosmological observations illustrate how light speed connects the smallest scales of quantum mechanics to the largest scales of cosmic structure. Quantum fluctuations that occurred when the universe was smaller than a subatomic particle eventually grew to span millions of light years, guided by the interplay between gravity, expansion, and the fundamental speed limit of space-time. The photons that carry this information to us have traveled across an expanding universe for nearly 14 billion years, their wavelengths gradually stretched by the growth of space itself. Yet they maintain their fundamental character as electromagnetic radiation, following the same physical laws that govern the light in your room and the radio waves carrying signals between cell phone towers. This universality of electromagnetic phenomena across all scales of space and time demonstrates the remarkable unity underlying the apparent diversity of natural phenomena. From the quantum interactions that bind atoms together to the cosmic radiation that fills all of space, electromagnetic fields operate according to the same fundamental principles, all unified by the constant speed at which they propagate through space-time. As you rest quietly in the gentle darkness, surrounded by the soft electromagnetic glow of artificial lights and warmed by thermal radiation from nearby objects, you're participating directly in this cosmic electromagnetic symphony. The photons reaching your eyes carry energy that was created through the same fundamental processes that power distant stars and galaxies, following the same universal laws that have governed the behavior of light throughout cosmic history. In the profound silence between one moment and the next, light continues its eternal journey through space and time, carrying information across vast distances at its unwavering cosmic speed. This constancy creates the framework within which all physical processes unfold, from the rapid oscillations of atoms to the slow evolution of galaxies across billions of years. The speed of light thus emerges not as an arbitrary limit imposed on the universe, but as a fundamental expression of the deepest symmetries and structures of space-time itself. It connects space with time, matter with energy, cause with effect, creating the logical and mathematical coherence that makes our universe comprehensible to conscious minds that have evolved within its gentle, persistent constraints. The gentle rhythm of electromagnetic waves surrounds you even now, as radio signals from distant transmitters traverse the space around your home. These invisible messengers travel through walls, through air, through the seemingly empty spaces between atoms, all moving at that same unwavering speed. The radio waves carrying music to a nearby device, the cellular signals connecting phones to distant towers, the Wi-Fi signals linking computers to the vast network of human knowledge. All of these follow the fundamental law that governs every electromagnetic phenomenon in the universe. Each radio wave is simply light of a different wavelength, stretched far beyond what human eyes can perceive, but following identical principles. A radio photon with a wavelength of several meters behaves according to the same electromagnetic equations as a visible light photon with a wavelength measured in nanometers. Both travel at precisely the same speed through vacuum, both carry energy proportional to their frequency, both interact with matter through the same fundamental forces. The radio telescope arrays scattered across Earth's surface detect these longer wavelengths from cosmic sources, billions of light-years distant. Pulsars, those rapidly spinning neutron stars, emit beams of radio waves that sweep across space like cosmic lighthouses. Each pulse arrives at Earth with clockwork precision, having traveled for years or decades at light speed through the near-perfect vacuum of interstellar space. These pulsar signals provide some of the most accurate clocks in the universe, their timing so precise that astronomers use them to detect the tiny gravitational wave distortions that ripple through space-time itself. When gravitational waves pass through our local region of space, they stretch and compress the fabric of space-time by amounts so small they would be imperceptible to any measurement except the most delicate timing of these cosmic beacons. The millisecond pulsars, spinning hundreds of times per second with the mass of the Sun compressed into a sphere just 20 kilometers across, maintain timing stability that rivals the best atomic clocks humans have ever constructed. Their radio beams, generated by charged particles spiraling around intense magnetic field lines, travel across vast distances without losing their temporal precision. This remarkable stability depends entirely on the constancy of light speed. If electromagnetic radiation could vary in velocity depending on its wavelength, frequency, or the conditions of space through which it travels, these pulsar signals would arrive at unpredictable times. The fact that we observe such precise timing from pulsars throughout our galaxy confirms that light speed remains constant across a wide range of cosmic environments. The magnetic fields around these neutron stars reach intensities trillions of times stronger than Earth's magnetic field, yet the radio waves they generate still propagate at exactly light speed once they escape into the surrounding space. Even in these extreme electromagnetic environments, the fundamental properties of space-time ensure that all forms of electromagnetic radiation maintain their characteristic velocity. The energy carried by these radio waves follows the same quantum principles that govern visible light. Each radio photon carries energy proportional to its frequency, though radio photons have much lower frequencies and therefore much less energy than visible light photons. A single radio photon from a distant pulsar might carry energy equivalent to only a tiny fraction of what a single optical photon carries, yet both follow identical propagation rules through space-time. When these radio waves encounter Earth's ionosphere, the charged particles in this upper atmospheric layer can affect their propagation speed slightly, causing different frequencies to arrive at slightly different times. This dispersion effect allows astronomers to measure the density of free electrons along the path between pulsar and Earth, providing insights into the structure of interstellar space. Yet even this atmospheric dispersion confirms the fundamental constancy of light speed in vacuum. The radio waves slow down only when traveling through a medium containing charged particles, exactly as predicted by Maxwell's equations. Once they escape back into vacuum, they immediately resume their characteristic speed, unchanged by their brief journey through denser matter. The study of these propagation effects reveals the remarkable emptiness of space between stars. Interstellar regions contain on average only about 1 atom per cubic centimeter, creating a vacuum far more perfect than anything achievable in terrestrial laboratories. Through this near emptiness, electromagnetic radiation of all wavelengths travels at the fundamental speed determined by the properties of space-time itself. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, provides another testament to light's unwavering speed across cosmic time. These photons have been traveling for nearly 14 billion years. Their wavelengths gradually stretched by the expansion of space, but their speed through local space-time remaining constant throughout their journey. As space expanded during their voyage, the wavelengths of these photons increased from the visible and infrared light they were when first emitted to the microwave radiation we detect today. This cosmological redshift preserves the total energy of each photon while distributing it across longer wavelengths, following the precise mathematical relationships predicted by general relativity and electromagnetic theory. The temperature of this cosmic background radiation, measured at 2.7 Kelvin above absolute zero, represents the current thermal state of the universe as a whole. This temperature corresponds to the peak wavelength of thermal radiation that fills all of space, a gentle electromagnetic glow that permeates every cubic centimeter of the observable universe. Even in the deepest intergalactic voids, regions where matter density drops to less than 1 atom per cubic meter across millions of light years, this background radiation maintains its characteristic temperature and spectrum. The photons that compose it continue their eternal journey through expanding space, cooling gradually as the universe grows larger, but never changing their fundamental speed. This cosmic radiation field provides a universal reference frame for the motion of galaxies and galaxy clusters throughout the universe. By measuring tiny variations in the temperature of this background radiation in different directions, astronomers can detect the motion of our entire local group of galaxies through space at several hundred kilometers per second, relative to this cosmic rest frame. These measurements reveal that even our own galaxy participates in large-scale flows of matter, driven by the gravitational attraction of massive structures beyond our immediate neighborhood. The cosmic web of galaxy filaments and vast empty voids creates gravitational fields that influence the motion of matter across hundreds of millions of light years, all connected by the patient propagation of gravitational and electromagnetic influences at light speed. The largest structures in the universe, galaxy superclusters containing thousands of individual galaxies, are bound together by gravitational forces that propagate at light speed across their enormous spans. Changes in the gravitational field at one edge of such a structure take millions of years to influence matter at the opposite edge, creating complex dynamical systems that evolve slowly over cosmic time. These massive structures themselves form through the gradual amplification of tiny density fluctuations that existed when the universe was young. Dark matter, that mysterious component that comprises about 27% of the cosmic energy budget, played a crucial role in this structure formation by providing the gravitational scaffolding around which ordinary matter could accumulate. The gravitational influences that shape these dark matter structures also propagated at light speed, ensuring that the growth of cosmic structure proceeded in a causally consistent manner. Regions of space that were not in causal contact, meaning that light speed signals could not have traveled between them, developed independently until the expansion of the universe brought them within each other's cosmic horizons. This causal structure of cosmic evolution explains why the universe appears so uniform on large scales, despite having formed from initially tiny quantum fluctuations. The processes that created this uniformity operated within the constraints imposed by light speed, smoothing out irregularities only within regions that could influence each other through light speed communications. The inflationary epoch in the very early universe provides a proposed solution to this horizon problem. If the universe underwent a brief period of exponential expansion when it was less than a tiny fraction of a second old, regions that appear causally disconnected today could have been in causal contact before inflation stretched them apart. During this hypothetical inflationary period, space itself expanded faster than light, carrying matter and energy along with it. This doesn't violate the cosmic speed limit because the expansion of space is not limited by the same constraints that govern the motion of matter and energy through space. The fabric of space-time itself can grow at any rate, while still preserving the fundamental speed limit for signals traveling through that expanding framework. The end of inflation would have left the universe filled with quantum fluctuations stretched to enormous scales, providing the seeds for all subsequent structure formation. These primordial fluctuations, amplified by gravity over billions of years, eventually grew into the galaxies, stars, and planets we observe today. Evidence for this inflationary scenario comes partly from the remarkable flatness of space on cosmological scales. Measurements of the cosmic microwave background reveal that the geometry of the universe follows Euclidean rules to extraordinary precision, suggesting that any initial curvature was stretched nearly flat during the inflationary expansion. The quantum fluctuations that inflation theory predicts should also have generated gravitational waves, ripples in space-time itself that propagate at light speed through the cosmos. These primordial gravitational waves would create a specific pattern of polarization in the cosmic microwave background radiation, providing a potential observational test of inflationary cosmology. Current and future observatories designed to detect these subtle polarization signals must account for the precise propagation of electromagnetic radiation from the surface of last scattering to Earth. The 14 billion-year journey of cosmic microwave background photons through expanding space creates systematic effects that must be carefully modeled to extract the tiny signals from primordial gravitational waves. The technology required for these measurements pushes the boundaries of precision electromagnetic detection. Superconducting detectors cooled to within millidegrees of absolute zero can sense individual microwave photons, measuring their energy and polarization with extraordinary accuracy. These detectors exploit quantum mechanical effects to achieve sensitivities that approach fundamental physical limits. The quantum nature of electromagnetic radiation becomes apparent in these ultra-sensitive measurements. Each microwave photon carries a discrete packet of energy determined by Planck's constant and the photon's frequency. The detection of individual photons reveals the particle nature of light, complementing the wave description that governs its propagation through space. This wave-particle duality of electromagnetic radiation represents one of the most profound insights of 20th century physics. Light exhibits wave-like behavior when propagating through space, following Maxwell's equations and traveling at the fundamental speed limit of spacetime. Yet light also exhibits particle-like behavior when interacting with matter, transferring discrete amounts of energy in quantum mechanical processes. The photoelectric effect, which earned Einstein his Nobel Prize, demonstrates this particle nature directly. When light strikes a metal surface, it can eject electrons with kinetic energies that depend only on the light's frequency, not its intensity. This observation can only be explained if light consists of particle-like photons, each carrying energy proportional to frequency. The energy of each photon equals Planck's constant multiplied by the frequency of the electromagnetic wave. This relationship connects the quantum mechanical description of light as particles to the classical description of light as waves, unifying two seemingly contradictory aspects of electromagnetic radiation. Higher frequency light, with shorter wavelengths, carries more energy per photon than lower frequency light. Gamma rays, with frequencies trillions of times higher than radio waves, carry millions of times more energy per photon. Yet all photons, regardless of their energy, travel at exactly the same speed through vacuum. This universality of photon velocity reveals the deep connection between electromagnetic radiation and the structure of space-time itself. The speed of light emerges not from any property specific to electromagnetic fields, but from the fundamental geometry of space and time. All massless particles, whether photons, gravitons, or hypothetical particles not yet discovered, must travel at this same cosmic speed limit. Gravitational waves, ripples in the fabric of space-time itself, propagate at light speed because they represent distortions in the very medium through which all signals travel. When two black holes spiral into each other and merge, they create gravitational waves that carry energy away from the system at light speed, causing the orbital decay that leads to the final collision. The detection of these gravitational waves by observatories like LIGO and Virgo opened an entirely new window on the universe, one that complements electromagnetic observations by providing information about events that produce little or no light. The collision of two black holes, for instance, generates powerful gravitational waves, but very little electromagnetic radiation that can escape the extreme gravitational fields near the event horizons. The simultaneous detection of gravitational waves and electromagnetic signals from the collision of two neutron stars in 2017 provided direct confirmation that these different types of signals travel at the same speed through space. The gravitational waves and gamma rays from this event arrived at Earth within seconds of each other after traveling for 130 million years across intergalactic space. This remarkable coincidence of arrival times confirmed theoretical predictions that gravitational and electromagnetic influences propagate at the same fundamental speed. If gravity traveled significantly faster or slower than light, the signals from cosmic events would be separated by years or decades, making multi-messenger astronomy impossible. The neutron star collision that produced both gravitational waves and electromagnetic radiation also created heavy elements through rapid neutron capture processes. The collision ejected material enriched with newly synthesized gold, platinum, and other heavy elements into the surrounding space at velocities reaching significant fractions of light speed. The electromagnetic radiation from this ejected material revealed its chemical composition through spectroscopic analysis. The characteristic wavelengths absorbed and emitted by heavy element atoms provided direct observational evidence for the nucleosynthesis processes occurring during neutron star mergers. This expelled material, traveling outward from the collision site at thousands of kilometers per second, will eventually slow down through interactions with the interstellar medium and become incorporated into future generations of stars and planets. The gold and other heavy elements created in this violent event may someday find their way into rocky planets, where they could be mined and shaped by intelligent civilizations billions of years in the future. The electromagnetic radiation announcing this cosmic alchemy travels much faster than the expelled matter itself, carrying news of the heavy element creation across the galaxy at light speed. Radio telescopes, optical observatories, and gamma-ray detectors throughout the solar system detected this radiation within hours of the gravitational wave signal, allowing astronomers to study the aftermath of the collision in unprecedented detail. The fading electromagnetic afterglow of the neutron star merger followed predictions based on models of radioactive decay and thermal emission from the expanding debris cloud. As the ejected material expanded and cooled, the peak wavelength of its thermal radiation shifted toward longer wavelengths, creating a predictable sequence of observations across the electromagnetic spectrum. These observations confirmed theoretical models of heavy element nuclear synthesis and provided insights into the equation of state of matter at nuclear densities. The behavior of neutron star material under extreme conditions of temperature, pressure, and magnetic field strength can only be studied through astronomical observations of these rare cosmic events. The magnetic fields generated during neutron star collisions can reach intensities that exceed laboratory capabilities by many orders of magnitude. In these extreme electromagnetic environments, quantum effects become important for the behavior of charged particles and the propagation of electromagnetic radiation. Yet even in these exotic conditions, far beyond anything achievable on Earth, electromagnetic radiation continues to propagate at light speed once it escapes the immediate collision region. The fundamental constants that determine this speed appear to remain unchanged even in the most extreme astrophysical environments known to exist. The constancy of these fundamental constants across space and time provides one of the strongest supports for our current understanding of physics. Spectroscopic observations of distant galaxies show that the fine structure constant, which determines the strength of electromagnetic interactions, has remained unchanged for billions of years of cosmic evolution. This stability of physical constants suggests that the laws of nature themselves possess a robustness that transcends the particular conditions found in any specific time or place. The speed of light, as one of these fundamental constants, appears to represent a truly universal property of space-time that governs the behavior of matter and energy throughout the observable universe. As you rest quietly in the gentle darkness, perhaps becoming aware of the soft electromagnetic glow from nearby electronic devices, you're witnessing the local manifestation of these same universal principles. The light-emitting diodes in digital displays create photons through the same quantum mechanical processes that power distant stars, though at much lower energies and intensities. The electrons in these semiconductor devices drop from higher energy states to lower ones, releasing their excess energy as photons of specific wavelengths determined by the electronic structure of the material. These photons immediately begin traveling at light speed through the air toward your eyes, carrying information about the device's display in the form of modulated electromagnetic radiation. Your retina detects these photons through photoreceptor cells that have evolved exquisite sensitivity to electromagnetic radiation in the visible spectrum. The rhodopsin molecules in these cells undergo conformational changes when struck by photons, triggering neural signals that your brain interprets as vision. This biological detection of electromagnetic radiation operates according to the same quantum mechanical principles that govern all photon-matter interactions. Each photon absorbed by a rhodopsin molecule transfers its energy instantaneously, causing molecular changes that initiate the complex cascade of biochemical reactions underlying visual perception. The speed at which these neural signals propagate through your visual system is limited not by light speed, but by the much slower velocity of electrochemical signals along nerve fibers. While the photons travel from source to retina at 300,000 kilometers per second, the resulting neural impulses move through your optic nerve at only about 100 meters per second. This vast difference in signal speeds illustrates how electromagnetic phenomena operate on fundamentally different timescales than biological processes. The light reaching your eyes completes its journey almost instantaneously, while the neural processing of that visual information requires milliseconds to tens of milliseconds. Even the biochemical reactions within your cells operate according to principles ultimately governed by electromagnetic forces propagating at light speed. The molecular bonds that hold proteins in their functional conformations depend on electromagnetic interactions between atoms, with changes in bond configurations propagating through molecular structures at velocities determined by the speed of light. The thermal motion of molecules in your body generates a continuous background of infrared radiation that carries away excess heat at light speed. This thermal regulation depends on the precise balance between heat generation through metabolism and heat loss through electromagnetic radiation, conduction, and convection. The infrared photons emitted by your skin travel outward through the surrounding air, carrying thermal energy away from your body and contributing to the electromagnetic environment of your immediate surroundings. These photons follow the same propagation rules as visible light, though their longer wavelengths make them invisible to human eyes. Specialized infrared cameras can detect this thermal radiation, creating images that reveal the temperature distribution across your body's surface. The warmest regions appear brightest in such images, while cooler areas appear dimmer, all determined by the intensity of electromagnetic radiation at infrared wavelengths. This thermal imaging technology exploits the direct relationship between temperature and electromagnetic radiation described by Planck's law of blackbody radiation. Every object with a temperature above absolute zero emits electromagnetic radiation with a spectrum determined entirely by its temperature, with hotter objects emitting more total energy and peaking at shorter wavelengths. The Sun's surface temperature of approximately 5,800 Kelvin produces electromagnetic radiation that peaks in the visible spectrum, explaining why human eyes evolved sensitivity to these particular wavelengths. The thermal radiation from your body, at a temperature near 300 Kelvin, peaks in the far infrared region around 10 micrometers wavelength. This biological attunement to solar radiation wavelengths represents an evolutionary adaptation to the electromagnetic environment of Earth's surface. The atmosphere filters out most ultraviolet radiation while transmitting visible light efficiently, creating a natural window for photosynthesis and vision that has shaped the development of life on our planet. The chlorophyll molecules that power photosynthesis absorb specific wavelengths of visible light, using this electromagnetic energy to drive chemical reactions that convert carbon dioxide and water into sugars and oxygen. These photochemical processes operate through quantum mechanical transitions that occur when chlorophyll molecules absorb photons of appropriate energies. The efficiency of photosynthesis depends critically on the precise matching between chlorophyll's absorption spectrum and the wavelengths of light available at Earth's surface. This remarkable correspondence between stellar radiation, atmospheric transmission, and biological chemistry illustrates the deep connections between electromagnetic phenomena and the emergence of life in the universe. Similar photochemical processes may occur on planets orbiting other stars, though the details would depend on the spectral characteristics of each particular stellar system. Red dwarf stars, which comprise the majority of stars in our galaxy, emit most of their energy at longer wavelengths than our Sun, potentially requiring different photosynthetic strategies for any life forms that might develop in such systems. The light from these distant stellar systems carries information about their composition, temperature, and planetary environments across interstellar distances at light speed. Future space-based telescopes may be able to detect biosignature gases in the atmospheres of nearby exoplanets by analyzing the spectrum of starlight that passes through these alien atmospheres. Such observations would rely on the same spectroscopic principles that allow us to study the composition of distant stars and galaxies. When light passes through a gas, atoms and molecules absorb photons at specific wavelengths corresponding to their electronic and vibrational energy levels, creating dark absorption lines in the spectrum. The detection of oxygen, water vapor, methane, and other potential biosignature molecules in exoplanet atmospheres would provide indirect evidence for biological processes operating on worlds many light years from Earth. The photons carrying this information would have traveled for years or decades at light speed, bringing news of potentially habitable environments across the vast distances between stars. The search for life beyond Earth thus depends fundamentally on the constancy of light speed and the universal nature of electromagnetic radiation. The same physical laws that govern the emission and absorption of light by atoms and molecules on Earth apply equally to matter throughout the universe, enabling remote analysis of cosmic environments through spectroscopic techniques. This universality of physical law, confirmed through countless astronomical observations, suggests that the speed of light represents a truly fundamental constant that constrains the behavior of matter and energy everywhere in the observable universe. No observation has ever revealed a variation in light speed or other fundamental constants across the enormous range of environments found in cosmic space. As you settle deeper into the quiet comfort of your surroundings, the electromagnetic radiation continuing to flow gently around you serves as a constant reminder of your connection to these vast cosmic processes. The same fundamental forces that power distant stars and galaxies operate on molecular scales within your own body, all unified by the unchanging speed at which electromagnetic influences propagate through space-time. In the soft darkness, punctuated perhaps by the gentle glow of electronic displays or distant streetlights, you rest within an ocean of electromagnetic radiation that connects every atom in your body to every star in the visible universe. This connection operates not through mystical forces or conscious intent, but through the patient, unwavering propagation of electromagnetic fields at their characteristic cosmic velocity. The photons reaching your eyes tonight began their journeys at moments spanning from nanoseconds ago for nearby artificial lights, to years ago for the light of visible stars, to billions of years ago for the most distant galaxies observable through powerful telescopes. Each photon has traveled its entire distance at exactly the same speed, creating a temporal mosaic that reveals the history of electromagnetic processes throughout cosmic time. This grand electromagnetic symphony plays out continuously around you, mostly beyond the reach of human senses, but detectable through the sophisticated instruments that extend our perception across the full spectrum of electromagnetic radiation. From the longest radio waves to the most energetic gamma rays, all forms of electromagnetic radiation follow the same fundamental principles, all traveling at the same cosmic speed limit that defines the very structure of space-time itself. In the gentle quietude of this moment, as consciousness gradually releases its hold on the analytical mind and drifts toward the restorative embrace of sleep, consider how the speed of light creates the temporal framework within which all experience unfolds. Every sensation, every thought, every moment of awareness exists within the causal structure defined by light's unwavering velocity through the fabric of space and time. The boundaries of what we can know, what we can influence, and what can influence us are all determined by this fundamental speed limit that governs the flow of information through the universe. Beyond the cosmic horizon, defined by light's finite velocity, lies a realm forever hidden from direct observation, containing perhaps countless worlds and civilizations whose existence remains necessarily unknown to us across the vast expanses of space and time. Yet within the observable universe, light serves as our faithful messenger, carrying information across distances so vast they challenge human comprehension, all while maintaining its characteristic velocity with mathematical precision. Through this constant flow of electromagnetic radiation, we participate in the grand conversation of the cosmos, listening to stories written in starlight and learning about the fundamental nature of reality itself. As sleep approaches and consciousness gently fades, the speed of light continues its eternal role as the universe's timekeeper, setting the pace for every physical process from the quantum mechanical transitions within atoms to the slow dance of galaxies across billions of years. In this cosmic rhythm, where light defines the very meaning of simultaneity and causality, we find our place as conscious observers embedded within a universe governed by elegant mathematical laws and profound physical principles. The last thought before sleep might be one of quiet wonder at the remarkable fact that the same speed limit that governs the most distant quasars and the most ancient light in the universe also governs the gentle electromagnetic glow that surrounds you now, creating a continuous thread of physical law that connects the most intimate moments of human experience to the grandest scales of cosmic evolution, all unified by the patient, eternal constancy of light traveling through the infinite darkness at its characteristic and unchanging speed. The electromagnetic symphony that surrounds you extends far beyond the visible spectrum, reaching into realms of radiation that human senses cannot directly perceive. Radio waves from distant galaxies wash over you continuously, carrying whispers of cosmic events that occurred billions of years ago. These gentle messengers travel at precisely the same speed as the light illuminating your room, yet their wavelengths stretch across meters rather than the tiny fractions of meters that characterize visible light. Consider the radio telescope arrays positioned across remote landscapes. Their massive dishes turn skyward in silent vigil. These instruments detect electromagnetic radiation with wavelengths thousands of times longer than visible light. Yet this cosmic radio energy follows identical propagation laws. A radio photon emitted by a quasar 12 billion light-years away travels through the expanding universe at exactly the same velocity as the infrared radiation warming your skin from a nearby heater. This universality of electromagnetic speed reveals something profound about the underlying structure of reality. The speed limit that governs light is not specific to any particular wavelength or frequency of electromagnetic radiation. Instead, it represents a fundamental property of the medium through which all electromagnetic disturbances propagate, the fabric of space-time itself. The mathematical relationship between wavelength and frequency remains constant across the entire electromagnetic spectrum, bound together by the speed of light in a simple but elegant equation. As wavelength increases, frequency decreases in perfect inverse proportion, ensuring that their product always equals that fundamental velocity of electromagnetic propagation through vacuum. Radio astronomers exploit this relationship to study the universe across cosmic time. The hydrogen atom, the most abundant element in the cosmos, emits radio waves at a characteristic frequency when its electron flips between spin states. This 21 centimeter radiation provides a cosmic beacon that allows astronomers to map the distribution of hydrogen throughout space and time. When this hydrogen radiation travels from distant galaxies toward Earth, the expansion of the universe gradually stretches its wavelength, shifting the characteristic 21 centimeter signal to longer wavelengths. By measuring this cosmological redshift, astronomers can determine both the distance to the source and the rate of cosmic expansion when the radiation was first emitted. These radio observations reveal vast structures of neutral hydrogen gas extending across millions of light years, the raw material from which future generations of stars will form. The radio waves carrying this information have traveled for billions of years at light speed, bringing news of cosmic evolution from epochs when the universe was young and galaxies were just beginning to take their current forms. The same electromagnetic principles that govern these cosmic radio signals also control the operation of every electronic device in your vicinity. The alternating current flowing through electrical circuits creates electromagnetic fields that oscillate at precisely controlled frequencies, whether in the 60 Hz alternation of household power or the gigahertz frequencies of computer processors. These electromagnetic fields propagate through conducting materials at velocities that approach but never quite reach the speed of light in vacuum. The presence of matter slightly slows electromagnetic propagation, creating the small delays that electrical engineers must account for in high-speed digital circuits. Even the simple act of turning on a light switch initiates electromagnetic waves that propagate through the wiring at nearly light speed, carrying the signal that completes the electrical circuit. This signal travels much faster than the physical motion of electrons through the conductor, which drift along at speeds measured in millimeters per second. The distinction between signal velocity and particle velocity illustrates a fundamental aspect of electromagnetic propagation. Information and energy can travel at light speed through matter, even when the individual charge carriers move much more slowly. This principle enables the rapid communication that underlies modern technology, from telephone networks to internet infrastructure. Optical fibers exploit this principle to carry information at significant fractions of light speed across vast distances. Laser light modulated with digital signals propagates through specially designed glass fibers, with the light itself traveling at about 2/3 the speed it would achieve in vacuum due to the refractive properties of the glass medium. These fiber optic networks span continents and ocean basins, carrying electromagnetic signals that connect distant regions of Earth through pathways that follow the curvature of the planet's surface. The signals arrive with delays measured in milliseconds for transcontinental distances, creating the nearly instantaneous global communications that define modern civilization. The undersea cables that carry these optical signals rest on ocean floors thousands of meters below the surface, protected from the dynamic environment of surface waters. Yet even at these depths, the fundamental laws governing electromagnetic propagation remain unchanged. Light travels through the fiber optic cores at its characteristic velocity, limited only by the material properties of the transmission medium. Satellites orbiting high above Earth's atmosphere provide another pathway for electromagnetic communication, using radio waves that travel through the near vacuum of space at full light speed. The round-trip delay for signals transmitted to geostationary satellites, positioned 36,000 kilometers above the equator, amounts to about a quarter of a second, a noticeable pause in real-time conversations that reflects the finite speed of electromagnetic radiation. These communication delays, barely perceptible in everyday experience, become significant for spacecraft exploring the outer regions of the solar system. Radio signals transmitted to the Voyager spacecraft, now traveling in interstellar space beyond the influence of the solar wind, require more than 20 hours to cross the vast distance separating Earth from these distant explorers. The patient journey of these radio signals across billions of kilometers of space illustrates the enormous scales involved in interplanetary communication. Each command sent to a distant spacecraft must be transmitted hours or days before it is needed, accounting for the travel time required for electromagnetic signals to traverse the solar system at light speed. When these spacecraft respond with scientific data about their distant environments, their radio transmissions begin another long journey back to Earth at the same unwavering velocity. The information they carry about magnetic fields, particle densities, and cosmic ray intensities in the outer solar system arrives as electromagnetic waves that have traveled for hours through the near-perfect vacuum between worlds. The Deep Space Network, a collection of large radio telescopes positioned around Earth, maintains continuous communication with these distant explorers. As Earth rotates, different antennas take over the task of receiving the faint radio signals, ensuring that the electromagnetic link between Earth and its robotic ambassadors remains unbroken despite the vast distances involved. These radio signals arrive at Earth with power levels billions of times weaker than a typical cell phone transmission. Yet sophisticated amplification and signal processing techniques can extract meaningful information from electromagnetic waves that carry only a few photons per second. Each detected photon represents a tiny packet of information that has traveled across the solar system at light speed. The weakness of these signals illustrates an important property of electromagnetic radiation. Its intensity decreases with the square of the distance from its source. A radio signal that travels twice as far spreads its energy over 4 times as much area, reducing the power received by any particular antenna by a factor of 4. This inverse square law governs all forms of electromagnetic radiation, from radio waves to visible light to gamma rays. It explains why distant stars appear dimmer than nearby ones of similar intrinsic brightness, and why radio telescopes require such large collecting areas to detect faint signals from cosmic sources. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, follows this same inverse square relationship as it propagates through expanding space. Though this radiation fills the universe uniformly, its intensity has decreased over cosmic time, as the expansion of space has diluted its energy density and stretched its wavelengths toward longer values. The current temperature of this background radiation, measured at 2.7 Kelvin above absolute zero, represents the thermal state of the universe as a whole after nearly 14 billion years of expansion and cooling. This electromagnetic fossil carries within its subtle temperature variations, the imprint of density fluctuations that existed when the universe was only 380,000 years old. Advanced satellite observatories have mapped these temperature fluctuations across the entire sky with extraordinary precision, revealing patterns that encode information about the fundamental parameters governing cosmic evolution. The angular scale of these fluctuations depends on the geometry of spacetime and the expansion history of the universe itself. These observations confirm that we live in a universe whose large-scale geometry follows the familiar rules of Euclidean space, a remarkable result that emerges from precise measurements of electromagnetic radiation that has traveled for nearly the entire age of the cosmos. The photons carrying this information began their journey when the universe was a hot, dense plasma cooling rapidly as space expanded. The moment of their creation marks the epoch when the universe became transparent to electromagnetic radiation for the first time. Before this recombination event, free electrons scattered photons efficiently, making the cosmos opaque to light. The cosmic microwave background shows us the universe at the moment it cleared, like fog lifting to reveal a distant landscape. The journey of these ancient photons through expanding space-time illustrates another profound aspect of light's relationship to cosmic evolution. As space grew larger during their voyage, the wavelengths of the photons stretched proportionally, shifting from the visible and infrared light they were when first emitted to the microwave radiation we detect today. This cosmological redshift preserves the fundamental character of electromagnetic radiation, while recording the history of cosmic expansion in the stretched wavelengths of ancient light. Each photon serves as a messenger, carrying information about the rate of expansion during its 14 billion year journey through space. The precise measurement of this ancient light has revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe appears to be accelerating, rather than slowing down under the influence of gravity. This acceleration is attributed to dark energy, a mysterious component that comprises about 70% of the cosmic energy budget. Dark energy manifests itself only through its gravitational effects on the expansion of space, causing distant supernovae to appear dimmer than expected based on their redshift. This dimming indicates that these stellar explosions are farther away than they would be in a universe expanding at a constant rate, providing evidence for cosmic acceleration. The light from these distant supernovae carries information about cosmic expansion rates billions of years ago, when dark energy first began to dominate over matter and radiation in driving the universe's growth. By comparing ancient expansion rates to more recent ones, astronomers can trace the history of cosmic acceleration and attempt to understand the nature of dark energy itself. These observations depend entirely on the assumption that electromagnetic radiation has traveled at constant speed throughout cosmic history. If the speed of light had changed over billions of years, our interpretations of astronomical observations would need fundamental revision. Yet every test of this assumption, from laboratory measurements to astronomical observations spanning cosmic time, confirms that light speed has remained constant within the precision of measurement. The constancy of this fundamental speed appears to be as enduring as the cosmos itself. This stability extends to all the fundamental constants that govern electromagnetic interactions. The fine structure constant, which determines the strength of electromagnetic forces, shows no evidence of variation across space or time. The charge and mass of electrons and protons appear identical in distant galaxies, billions of light-years away. The universality of these physical constants suggests that the laws of nature possess a robustness that transcends local conditions. The same electromagnetic principles that operate in terrestrial laboratories apply equally to the most exotic environments in the universe, from the surfaces of neutron stars to the accretion disks around supermassive black holes. Even in these extreme astrophysical environments, where magnetic fields reach intensities trillions of times stronger than Earth's field, and matter exists at densities comparable to atomic nuclei, electromagnetic radiation continues to propagate at its characteristic speed once it escapes into surrounding space. The study of such exotic objects provides natural laboratories for testing physical theories under conditions impossible to achieve on Earth. Pulsars, those rapidly spinning neutron stars with magnetic fields of unimaginable strength, emit beams of radio waves with timing precision that rivals the best atomic clocks ever constructed. These cosmic beacons allow astronomers to test Einstein's theories of relativity with extraordinary precision. The orbital decay of binary pulsar systems, caused by energy loss to gravitational radiation, matches theoretical predictions to better than 1 part in 1,000, confirming that gravitational waves propagate at precisely light speed. The recent direct detection of gravitational waves by observatories like LIGO has opened an entirely new window on the universe, one that complements electromagnetic observations by providing information about events that produce little or no light. The merger of two black holes generates powerful gravitational waves, but virtually no electromagnetic radiation that can escape their intense gravitational fields. When gravitational waves and electromagnetic signals from the same cosmic event reach Earth simultaneously, as occurred with the neutron star collision observed in 2017, they provide direct confirmation that these different types of disturbances propagate at identical speeds through spacetime. The arrival of both signals within seconds of each other after traveling for over 100 million years across space represents a remarkable validation of theoretical predictions. This multi-messenger astronomy reveals cosmic events with unprecedented detail, combining information carried by electromagnetic radiation with the complementary data encoded in gravitational wave signals. Each type of radiation follows the fundamental speed limit that governs all forms of energy and information propagation through the fabric of space-time. The neutron star collision that produced both gravitational waves and electromagnetic radiation also created heavy elements through rapid neutron capture processes that occur only in the most extreme environments. The electromagnetic afterglow of this event revealed the characteristic signatures of newly synthesized gold, platinum, and other heavy elements being ejected into space. The gold in any jewelry you might possess was likely forged in such a cosmic collision billions of years ago. its atoms assembled through nuclear processes that occurred in conditions of unimaginable violence and density. The light announcing this creation event began its journey across space at the moment of synthesis, carrying news of cosmic alchemy at the fundamental speed of electromagnetic propagation. This cosmic recycling of matter depends on electromagnetic processes operating across vast scales of space and time. When massive stars exhaust their nuclear fuel and explode as supernovae, the intense radiation pressure from the explosion drives stellar material outward into interstellar space at velocities that can reach significant fractions of light speed. The shock waves from these stellar explosions propagate through the surrounding interstellar medium, compressing gas and dust clouds and triggering the formation of new generations of stars. The electromagnetic radiation from the explosion travels much faster than the expanding shock wave, announcing the stellar death across the galaxy at light speed. Radio telescopes can detect the expanding shells of hot gas surrounding supernova remnants, revealing the structure of these cosmic recycling centers through observations of their characteristic radio emissions. The synchrotron radiation produced by high-energy electrons spiraling around magnetic field lines creates radio signals that astronomers can map to study the dynamics of stellar explosions. These radio observations reveal that supernova remnants continue to emit electromagnetic radiation for thousands of years after the initial explosion, as the expanding shockwave interacts with surrounding material. The radio waves carrying this information travel at light speed through interstellar space, bringing news of ongoing stellar evolution to telescopes throughout the galaxy. The interstellar medium through which these radio waves propagate consists primarily of hydrogen gas, with an average density of about 1 atom per cubic centimeter. This creates a vacuum far more perfect than anything achievable in terrestrial laboratories. Yet even this near emptiness can slightly affect the propagation of electromagnetic radiation. The free electrons scattered throughout interstellar space cause radio waves of different frequencies to travel at slightly different speeds, an effect called dispersion that becomes more pronounced for lower frequency radiation. By measuring the time delays between radio pulses at different frequencies, astronomers can determine the density of free electrons along the path between Source and Earth. These dispersion measurements provide insights into the structure of the galaxy's magnetic field and the distribution of ionized gas throughout interstellar space. The precise timing of radio pulses from pulsars allows astronomers to map the three-dimensional structure of the galactic magnetic field with remarkable detail. The magnetic field that threads through interstellar space plays a crucial role in star formation by providing support against gravitational collapse in giant molecular clouds. These vast reservoirs of cold gas and dust, some containing enough material to form hundreds of thousands of stars, are held together by the delicate balance between gravity and magnetic pressure. When portions of these molecular clouds begin to collapse under their own gravity, the infalling matter must somehow shed the magnetic field lines that initially provided support. This process, still not fully understood, allows dense cores to form within the clouds, eventually becoming hot enough to ignite nuclear fusion and birth new stars. The electromagnetic radiation from newly formed stars begins its journey through space at the moment fusion reactions commence in their cores. Young stars often exhibit violent outbursts and powerful stellar winds that create expanding bubbles of hot gas in their surrounding environment. These stellar nurseries glow brightly in infrared radiation as dust grains heated by starlight re-emit their absorbed energy at longer wavelengths. Space-based infrared telescopes can peer through the dust that obscures these regions in visible light, revealing the ongoing process of star formation in unprecedented detail. The infrared radiation from these star-forming regions follows the same propagation laws as visible light. traveling at light speed through space, but revealing aspects of cosmic evolution invisible to optical telescopes. Different wavelengths of infrared radiation trace different components of the star formation process, from the coldest dust clouds to the warm regions around newly ignited protostars. The Spitzer Space Telescope and its successor, the James Webb Space Telescope, have revolutionized our understanding of star formation by observing these processes in infrared light. The electromagnetic radiation they detect has traveled for years, decades, or centuries from nearby star-forming regions, carrying information about the birth of stars and planetary systems. The formation of planetary systems around young stars involves complex interactions between electromagnetic radiation, gravity, and the dynamics of orbiting material. The intense stellar wind from a newly formed star can blow away the lightest elements from the surrounding protoplanetary disk, leaving behind the heavier materials that eventually condense into rocky planets. The electromagnetic radiation pressure from the central star also affects the distribution of dust and gas in the protoplanetary disk, creating gaps and spiral structures that may guide the formation of planets. These radiation pressure effects operate through the momentum carried by photons, demonstrating another aspect of light's dual-wave particle nature. Each photon carries a tiny amount of momentum proportional to its energy, and when billions of photons strike dust grains in the protoplanetary disk, they can exert measurable forces that affect the orbital motion of small particles. This radiation pressure can either push particles outward from the star or, in combination with other forces, cause them to spiral inward toward the central star. The balance between radiation pressure, gravity, and gas drag determines the fate of dust grains in protoplanetary disks. Particles that survive this complex dynamical environment can stick together through electromagnetic forces, gradually building up larger objects that eventually become asteroids, comets, and planets. The electromagnetic forces that bind atoms together also govern the chemical processes that occur as these particles collide and merge. Van der Waals forces, arising from quantum mechanical fluctuations in electron distributions, allow dust grains to stick together even in the cold vacuum of space. These same electromagnetic forces operate within your body at this very moment, holding together the complex molecules that enable biological processes. The proteins that carry out cellular functions maintain their shapes through intricate networks of electromagnetic interactions between amino acids, creating the three-dimensional structures necessary for life. The chemical bonds that link atoms together in these biological molecules form and break according to quantum mechanical principles that involve the electromagnetic interaction between electrons and atomic nuclei. These processes occur at timescales much faster than human perception, yet they follow the same fundamental laws that govern electromagnetic radiation propagating through cosmic space. The energy required for these molecular processes comes ultimately from the electromagnetic radiation of distant stars, particularly our own sun. Photosynthesis captures solar energy and converts it into chemical form, creating the molecular fuel that powers virtually all life on Earth. The chlorophyll molecules responsible for photosynthesis absorb specific wavelengths of visible light, using this electromagnetic energy to drive chemical reactions that split water molecules and combine carbon dioxide into sugars. These photochemical processes represent one of the most important examples of electromagnetic radiation directly powering biological activity. The efficiency of photosynthesis depends on the precise matching between the absorption spectrum of chlorophyll and the wavelengths of light available at Earth's surface. This remarkable correspondence between stellar radiation and biological chemistry suggests deep connections between electromagnetic phenomena and the emergence of life. The same photochemical principles that enable photosynthesis also govern the operation of your visual system. When light enters your eyes, photons strike rhodopsin molecules in retinal photoreceptor cells, triggering conformational changes that initiate the cascade of neural signals underlying vision. Each photon absorbed by a rhodopsin molecule transfers its energy instantaneously, demonstrating the quantum mechanical nature of electromagnetic radiation at the molecular level. The detection of individual photons by biological systems approaches the theoretical limits of sensitivity possible for any light-detecting mechanism. This exquisite sensitivity to electromagnetic radiation allows biological organisms to extract information from remarkably faint light sources. Nocturnal animals can detect starlight levels corresponding to only a few photons per second reaching each photoreceptor cell, enabling vision under conditions that seem impossibly dark to human perception. The electromagnetic radiation that enables this night vision has traveled for years or decades from distant stars at light speed through interstellar space. The photons that allow an owl to hunt by starlight began their journey when nuclear fusion reactions in stellar cores converted hydrogen to helium, releasing energy that eventually escaped as electromagnetic radiation. This stellar light carries with it information about the physical conditions in stellar atmospheres, encoded in the precise wavelengths at which atoms and molecules absorb and emit radiation. Astronomers can decode this spectroscopic information to determine stellar temperatures, compositions, and motions through space. The Doppler shift of spectral lines reveals whether stars are moving toward or away from Earth, and by how much. This information has led to the discovery of thousands of exoplanets through their gravitational effects on the motion of their host stars, detected as tiny periodic shifts in stellar spectra. The light curves of these host stars, measured with extraordinary precision by space-based observatories, can reveal the presence of orbiting planets as they transit across the stellar disk. These transit events cause minute decreases in the star's apparent brightness, lasting only a few hours, but detectable through careful photometric analysis. The electromagnetic radiation dimmed by these planetary transits has traveled for years or decades at light speed from distant stellar systems. Each transit observation provides a snapshot of an alien world passing between its star and Earth, revealing information about planetary size, orbital period, and atmospheric composition. Atmospheric characterization of exoplanets relies on spectroscopic analysis of starlight that has passed through planetary atmospheres during transit events. Different molecules absorb specific wavelengths of electromagnetic radiation, creating characteristic signatures that can be detected in the transmitted starlight. The James Webb Space Telescope has revolutionized exoplanet atmosphere studies by observing in infrared wavelengths where many important atmospheric molecules have strong absorption features. Water vapor, carbon dioxide, methane, and other gases create distinctive patterns in infrared spectra that reveal the chemical composition of distant planetary atmospheres. These observations provide insights into the potential habitability of exoplanets by revealing whether they possess atmospheres capable of supporting liquid water on their surfaces. The detection of water vapor in exoplanet atmospheres represents one of the most exciting frontiers in the search for life beyond Earth. The electromagnetic radiation carrying this atmospheric information began its journey at the surface of distant stars, traveled through the thin atmospheres of orbiting planets, and then continued across interstellar space for years or decades before reaching terrestrial telescopes. Each photon serves as a messenger carrying news of potentially habitable worlds around other stars. The search for biosignature gases in exoplanet atmospheres represents the next frontier in this cosmic detective work. Oxygen, ozone, and other gases that might indicate biological activity could potentially be detected through careful spectroscopic analysis of atmospheric transmission spectra. Such discoveries would represent one of the most profound scientific achievements in human history, revealing that life exists beyond Earth through the patient analysis of electromagnetic radiation that has traveled across the vast distances between stars. The confirmation would arrive encoded in the subtle absorption features of starlight that has passed through an alien biosphere. Even if such biosignatures are never detected, the search itself demonstrates the remarkable power of electromagnetic radiation to carry information across cosmic distances. Every photon that reaches Earth from space brings with it a story of its origin, whether from stellar atmospheres, planetary surfaces, or the cosmic microwave background itself. The cumulative effect of countless photons arriving from throughout the observable universe creates a vast database of information about cosmic evolution, stellar physics, planetary science, and potentially astrobiology. This electromagnetic library spans the entire history of the universe, from the ancient afterglow of the Big Bang to the light of stars forming today. The organization of this cosmic information follows the fundamental constraint imposed by light's finite speed. We can never observe the universe as it exists now, but only as it was when the light we detect began its journey toward Earth. This creates a natural time machine that allows us to study cosmic evolution by looking deeper into space. The most distant galaxies observable by current telescopes appear as they were when the universe was only a few % of its current age. These ancient systems show us cosmic conditions during the epoch when the first stars and galaxies were forming, providing direct observational access to the early phases of cosmic evolution. The light from these distant galaxies has been traveling toward Earth for over 13 billion years, stretched by cosmic expansion until its wavelengths lie far in the infrared portion of the electromagnetic spectrum. Advanced space telescopes can detect this ancient radiation and use it to study the formation and evolution of the first cosmic structures. These observations reveal that galaxy formation began surprisingly early in cosmic history, with massive galaxies already assembled when the universe was less than 1 billion years old. The electromagnetic radiation from these early galaxies carries information about the first generations of stars and the initial enrichment of the cosmos with heavy elements. The study of cosmic chemical evolution through electromagnetic observations shows how the universe gradually transformed from a simple mixture of hydrogen and helium into the complex chemical environment we observe today. Each generation of stars added heavier elements to the cosmic mix, building up the periodic table through nuclear processes in stellar cores and explosive events. This cosmic enrichment process continues today as new stars form, evolve, and eventually return processed material to the interstellar medium. The electromagnetic radiation from these ongoing processes provides real-time updates on stellar evolution and nucleosynthesis throughout the local universe. The light from nearby galaxies has traveled for millions rather than billions of years, revealing more recent phases of cosmic evolution and star formation. These observations show that star formation rates have generally declined over cosmic time, as the universe has consumed much of its initial supply of star-forming gas. Current star formation occurs primarily in spiral galaxies, like our own Milky Way, where density waves compress interstellar gas and trigger the collapse of molecular clouds. The electromagnetic radiation from newly formed stars illuminates these spiral arms, creating the beautiful patterns visible in images of distant spiral galaxies. Our own galaxy participates in this ongoing star formation, with new stars being born in molecular cloud complexes throughout the galactic disk. The electromagnetic radiation from these stellar nurseries reaches us after traveling for hundreds or thousands of years at light speed through local interstellar space. The nearest star-forming regions lie close enough that we can study individual protostars and follow their evolution from initial collapse through the onset of nuclear fusion. These observations provide detailed insights into the star formation process that applies throughout the universe, revealed through electromagnetic radiation traveling at its fundamental cosmic speed. Even within our own solar system, electromagnetic radiation carries information about ongoing physical processes on planetary surfaces and in planetary atmospheres. The reflected sunlight from planets and moons reveals their surface compositions and atmospheric properties in the gentle quiet of this moment, as your mind begins to release its hold on conscious thought and drift toward the peaceful embrace of sleep. Perhaps you can sense the profound elegance of what we have discovered together. The speed of light is not simply a number in a physics textbook, nor a barrier imposed by some distant cosmic authority. It is the heartbeat of reality itself, the fundamental rhythm that connects every moment to the next, every cause to its effect, every star to every grain of sand. This cosmic speed limit emerges from the deepest structures of space and time, creating the framework within which all existence unfolds. It ensures that the universe remains logically coherent, that information flows in an orderly sequence from past to future, that consciousness itself can emerge and contemplate the elegant laws that gave it birth. Without this speed limit, causality would collapse, time would lose its meaning, and the very possibility of understanding would vanish into paradox. As you rest here in the soft darkness, surrounded by the gentle electromagnetic glow that connects you to distant stars and ancient galaxies, remember that you are part of something vast and beautiful and precisely ordered, the same light that allows you to see, the same electromagnetic forces that hold your atoms together, the same space-time that cradles your existence, all dance to the eternal rhythm set by this one unchanging constant. In the infinite darkness beyond your window, light continues its patient journey across cosmic distances, carrying stories of stellar birth and death, of galaxies forming and evolving, of the universe itself expanding and cooling according to laws written in the fundamental structure of reality. And in this gentle constancy, this unwavering reliability of light's speed, we find not a limitation, but a gift, the cosmic architecture that makes knowledge possible, that makes consciousness possible, that makes this very moment of peaceful understanding possible. Rest now, knowing that you are held within a universe governed by profound mathematical beauty, where every photon that ever was or ever will be travels at exactly the same speed, creating the temporal framework that allows the present moment to exist, allows you to exist, allows wonder itself to flourish in the gentle darkness of an infinite and perfectly ordered cosmos.